Fiber optic cable. Point number 1. Design of a fiber optic cable. Point number 2. A look inside a fiber optic cable. Point number 3. Will light pass through a bent fiber optic cable? Point number 4. Application. Point number 5. Light propagation inside fiber optic cable. Point number 6. Using fiber optic cable for communication. Structure of fiber optic cable. A fiber optic cable consists of a plastic sheath, which is the protective covering, an outer cladding, which is made of glass, and an inner core, which is made of glass. Optical fibers are very fine fibers of glass. They are as thin as a strand of hair. Optical fibers consist of a glass core surrounded by a glass cladding. Make use of total internal reflection to confine light within the core of the fiber. Act as a waveguide. The plastic sheath works as a protective covering for the glass cladding and core. Cladding serves to confine the light to the core and has a lower index of refraction. The protective sheath acts as shock absorber to protect the core and cladding from damage. The core of the fiber optic cable is not hollow but is a solid glass medium. The structure of fiber optic cable is more complex than shown previously. The cladding is also made up of pure silica glass. Coatings are usually multi-layers of plastics applied to preserve fiber strength, absorb shock, and provide extra fiber protection. These buffer coatings are available from 250 microns onward. Tight buffer consists of plastic layer over the basic fiber coating to withstand impact and crush. Strength members made of steel or Kevlar keep fibers free from stress by minimizing elongation and contraction. Cable jacket is made of various types of material. It protects fiber from weather, chemicals, and fire. In real life, optical fiber looks like any other cable, except that you cannot bend it too much. You would have seen it also in decorative applications like a lamp. Sectional views of the fiber optic cable. In the horizontal section, we can see a glass core, which is typically approximately 8.5 nanometer. We can see a glass cladding and a protective sheath. The protective sheath acts as shock absorber to protect the core and cladding from damage. The sheath usually comprises of a plastic material. Sometimes metallic sheaths are added for further physical protection. Propagation of light inside a fiber optic cable. The inner core is always optically denser than the outer cladding. Light injected into the core strikes the core cladding boundary at an angle greater than the critical angle, so is reflected back into the core. For a particular fiber optic cable, the critical angle between inner core and outer cladding always remains constant. Since both the angles of incidence and reflection are equal, the light ray continues to zigzag down the length of the fiber. In normal 90 degrees to surface, theta is equal to theta c. Theta dash is less than theta c. Theta c is equal to the critical angle. The light is therefore trapped within the core. Light striking the boundary at less than the critical angle passes into the cladding and is lost. The rays from the source travel from a rarer medium, which is air, to a denser medium, which is glass, and bend towards the normal. Angle theta c is the critical angle for the cable. All the rays entering the cable at an angle greater than angle theta c will be reflected instead of being refracted. All the rays entering the core at an angle greater than the critical angle of the cable will be transmitted to the other end through total internal reflection. The rays which enter the core at an angle less than the critical angle undergo refraction at the core cladding boundary and are lost. Why is angle theta I greater than angle theta c throughout the length of the cable? In a straight cable, the outer core surfaces are parallel, that is, AB is parallel to CD. N is perpendicular to AB and N dash is perpendicular to CD. Therefore, N is parallel to N dash. According to the laws of reflection, the angle of reflection will be equal to the angle of incidence. That is, angle theta I will be equal to angle theta R. Now, as N is parallel to N dash, therefore, angle theta I1 is equal to angle theta R, which are alternate angles. That is, the ray again strikes the surface at an angle greater than its critical angle and does so for each consecutive incidence to transmit through the cable. The rays entering the core at an angle less than the critical angle do not undergo total internal reflection and therefore are lost. Will the light reach the other end through the cable if it is bent? As the core is extremely thin, the number of reflections per unit length is high. Since distance between successive reflections is negligible, surface between two successive reflections are parallel. Consequently, all incident angles are greater than theta c. The slight bend, therefore, has no effect on the path of the trapped light. Is angle theta I greater than angle theta c when the cable is bent? The distance covered by the light in cable is so small that the surface AB and CD are parallel even when the cable is bent. According to the laws of reflection, theta I is equal to theta R. Therefore, theta I is greater than theta C. Therefore, theta R is greater than theta C. Therefore, AB is parallel to CD. Therefore, N is parallel to N dash. Theta I1 is equal to theta R, which are alternate angles. Theta I1 is greater than theta C. Hence, the incident angle is still greater than the critical angle. What happens when the cable is bent sharply? At this point, the incident angle is less than the critical angle. Consequently, some light is reflected and the rest escapes from the inner core. The amount of light escaping the inner core and that being reflected depends upon the sharpness of the bend. If it is too sharp, all of the light might escape the inner core. Applications of fiber optic cables. They are used in the field of medicine to view internal organs of the human body as in endoscopes. They are used in carrying information, sounds, words, images and data in the form of optical signals and impulses. They are used for decorative purposes, fancy lamps and colored water fountains which use the same property of trapping light as in fiber optics. Advantages of optical cables over conventional copper cables. Optical fibers have lower energy losses than current-carrying wires, particularly at higher frequencies, and can carry much more data. These fibers are lighter than metal wires, have greater flexibility, and are not affected by electromagnetic disturbances. Optical fibers connect the world through long-distance undersea cables. Communication through optical fibers. The optical fiber communication uses lasers. Lasers can produce very tightly focused pulses of light. Unlike a torch that spreads over in meters, lasers over thousands of kilometers will not spread more than few centimeters, and they can do it rapidly, many times a second. 3 green lasers are seen emanating from facilities at the Starfire Optical Range on Kirtland Air Force Base, New Mexico. Lasers used here to eliminate or minimize optical distortions caused by the Earth's atmosphere. The pulses are then picked up at the other end of the fiber by a light-sensitive cell that converts the pulses of light into pulses of electricity. These pulses of electricity are then fed into a computer that is digitized and decoded to reveal the message. Photodiode catches light, converts it to electricity. Phototransistor used as photodiode. Optical fibers, which are thinner than a human hair, work even when looped or bent around corners. Light remains contained within the walls of the fiber and does not disperse or radiate away. Since it is light, it travels at 300,000 kilometers per second. The communication is so fast that you can send an encyclopedia in a second. Optical cables have replaced copper in most of the countries. Copper cables suffer from losses in data as transmission is electrical in nature and depends on frequency. Therefore, transmission more than megabits per second is not possible. While in optical ones, being lossless, gigabits per second of bandwidth is possible. Copper cables are prone to electromagnetic interference such as that created when switching on a piece of electrical equipment, resulting data losses. Fiber optic cable can be laid next to power distribution cables and suffer no interference at all. Ground looping or transmission of electrical current through wire due to surges in electrical storm can fry our telecom equipments. Fiber optical cables are insulator by nature, as glass is an insulator, hence no electrical current passes through them.